Welcome to the course on Python for data analytics, machine learning and generative AI. In this session, we transition from descriptive analytics to predictive intelligence by introducing the foundations of machine learning. This session will cover bias versus variance, underfitting versus overfitting, linear regression, predicting continuous values, logistic regression, the probability of a category, regression evolution metrics, the confusion matrix and regularization. By the end of this session, you will be able to know the importance of generalization, linear and logistic regression and how to evaluate regression and classification models. In machine learning, we don't give the computer answers upfront. Instead, we give it data and a mission. The mission is learning. Unlike traditional programming, where rules are written by humans, a learning machine discovers rules or patterns on its own. Data becomes the fuel and patterns are the destination. By analyzing raw input, the machine identifies structure, relationships and trends, so it can be made accurate predictions in the future. To know whether a machine has truly learned, we must test its understanding. If we show it all the data at once, it might simply memorize instead of learning. So, we divide the data set into two parts. Typically, 80% becomes training data, the study material. The remaining 20% becomes testing data, the exam. This split allows us to check whether the model can apply what it learned to new, unseen examples. The true goal of machine learning is generalization. A good model doesn't just perform well on familiar data, it performs well on new data. During training, the model tries to capture the signal or pattern, the real underlying trend, by ignoring noise. Testing data simulates the real world. In the first phase, the model studies the training data and identifies a pattern that exhibits the relationships between inputs and outputs. The key action here is pattern identification. Once training is complete, the model faces the test data. The testing data has never been seen before by the model. Now, we ask a critical question. Can the model make accurate predictions using only what it learned? This step tells us whether the model has understood the pattern. Now, we will see the working of a machine learning model. We begin with raw data. This is the original information collected from sources like files, sensors, logs or user activity. At this stage, the data hasn't been used by the model yet. It's just stored and waiting to be processed. Next, the data is split into two parts. Training data, which is typically about 80% of the total data. Test data, which makes up the remaining 20%. The training set is used to teach the machine learning algorithm. During this phase, the model looks for patterns and relationships in the data. This process is called training, and it's where the model learns how to make predictions. Once training is complete, the model is not tested on the same data it learned from. Instead, we use the test data which the model has never seen before. This helps us understand how well the model can generalize to new, unseen data. The model makes the predictions on the test data. On those predictions are then compared with the actual correct answers. This step is called evaluation. To measure how well the model performs, we calculate a performance metrics such as accuracy. Accuracy tells us what percentage of predictions the model got right. Finally, based on this metrics, we can access the quality of the model. If the accuracy is high, the model is performing well. If it's low, we may need better data, different features, or a different algorithm. In an ideal world, every prediction would land preferably on the prediction line. In reality, that almost never happens. The difference between a model's prediction and the actual data point is called error. Error represents the portion of the data that doesn't fit neatly into the learned pattern, and understanding error is key to improving our models. Error occurring during testing the data is known as bias. Bias occurs when a model is too simple. Even during training, it struggles to fit the data properly. High bias means huge error. During training, the model consistently misses the underlying pattern. In this example, the data follows a curve, but the model insists on a straight line. Variance is the error occurring during testing the data. Here, the model performs extremely well on training data represented in blue dots, but fails on new unseen data represented in orange dots. This usually happens when the model is too complex, fitting not just the signal but also the noise. High variance means huge error during testing and poor generalization. The model memorized instead of learning. Model performance generally falls into one of the three categories. First, underfitting. The model is too simple. Second, overfitting. The model is too complex. And third, best fit. The model strikes the right balance. Our goal is always the middle ground, a model that captures the true pattern without chasing noise. Let's first see what underfitting is. Underfitting is a stage where the error is very high. During the training, the data giving high bias. It predicts a very simple pattern which is not able to accommodate all the data during training as well as testing. Hence, the model exhibits high training error, high bias, and high testing error, high variance. In overfitting, the model or the pattern is too complex. It fits every single data point perfectly, even the random noise in the data during training. At first glance, this looks impressive. The predictions line up exactly with the training points and the training accuracy is extremely high, giving less error or no error, which means low bias. However, this is actually a problem. The model is not learning underlying trend. Instead, it is memorizing the data, including fluctuations that don't represent real patterns. As a result, when new or unseen data is introduced, the model's performance drops sharply or creates high error during testing the data. This behavior is known as high variance. Small changes in input lead to large changes in output. In this state, the model achieves a balance between simplicity and complexity. The prediction curve does not try to pass through every data point. Instead, it smoothly follows the overall pattern in the data. This model has low bias, meaning it captures the true relationship accurately. Low variance, which means generalizes well to new data. This balance is often called the sweet spot in machine learning because the model focuses on the signal rather than the noise. It performs well not only on the training data but also on unseen test data. In machine learning, not all model errors are the same. One of the most important skills is diagnosing why a model fails. We see underfitting, also called high bias. The model is too simple to capture the underlying pattern in the data. As a result, it performs poorly on both training data and unseen test data. In the center is the ideal scenario, the best fit. The model is complex enough to learn meaningful patterns but simple enough to generalize. This balance produces low error on both training and test sets. We also see overfitting or high variance. Here, the model is too complex and starts memorizing noise instead of learning the true pattern. Training error is low, but test error is high. The goal is not complexity for its own sake, it's generalization. The objective of machine learning is predictive truth. Machine learning is not about forcing data to fit a predefined line. Instead, it's about discovering the structure that best reflects reality. This requires balancing two competing forces, bias and variance. Predictive truth lives at the balance point. Let's begin with linear regression, one of the simplest and most widely used supervised learning models. Linear regression predicts continuous values, meaning outputs like price, revenue or temperature. It maps input variables to an output using a straight line equation written as y is equal to mx plus b. Here, m represents the slope and b represents the intercept. The goal is to find the best fit line by minimizing prediction errors. These errors are called residuals, and the most common objective is minimizing mean squared error. Next is logistic regression, which is used for classification. Unlike linear regression, logistic regression predicts the probability that an input belongs to a category or usually class 0 or class 1. It uses a sigmoid function which converts any real number into a value between 0 and 1. Once the probability is calculated, the model applies a decision threshold, commonly 0.5. If the probability is above the threshold, the model predicts class 1, otherwise it predicts class 0. On comparing linear regression and logistic regression, linear regression is used when the output is continuous, such as predicting house prices. It produces values that can range from negative infinity to positive infinity and is usually trained using least squares estimation. Logistic regression is used when the goal is classification, such as spam detection. It outputs probability between 0 and 1 and is typically trained using maximum likelihood estimation. So, the key difference is the type of output, continuous prediction versus probability based classification. To measure how good a regression model is, we use evaluation metrics. Mean absolute error or MAE tells us the average size of errors and is more robust to outliers. Mean square error or MSE squares the errors, meaning it heavily penalizes large mistakes. Root mean square error or RMSE is simply the square root of MSE, bringing the error back into the original units, which makes it easier to interpret. Finally, R-square measure the goodness of fit, where 1 means perfect prediction and 0 means the model performs no better than predicting the average. For classification problems, accuracy alone can be misleading, especially when classes are imbalanced. That's why we use a confusion matrix. It divides predictions into 4 outcomes: true positives, false negatives and true negatives. From these, we calculate precision and recall. Precision tells us how many predicted positives were actually correct, useful when false positives are costly, like spam detection. Recall tells us how many actual positives were successfully identified, important when false negatives are dangerous, like disease detection. When precision and recall trade off against each other, we use additional metrics. The F1 score is the harmonic mean of precision and recall is the best when we want balance. The ROC curve and AUC measure how well the model distinguishes between classes across different thresholds. A higher AUC means better separation. Log loss evaluates the confidence of predictions and penalizes false confidence. In log loss, lower values indicate better performance. Regulations is a set of techniques in machine learning used to prevent overfitting and improve a model's ability to generalize to new unseen data. Overfitting occurs when a model learns the details and noise in the training data too well, leading to poor performance in real-world applications. Regularization addresses this by adding a penalty term. Imagine a student who memorizes their textbooks word by word, including all the specific examples and typos. When they take the actual exam, if the questions are slightly different from the examples in the book, they struggle because they only learn specific details, not the underlying concepts. They are too complex and rigid. A smart student learns the general concepts and principles, ignoring the tiny specific details, the noise. This student performs much better on the test even if the questions are new or slightly different because they understand the bigger picture. The penalty term is essentially the incentive that makes the model act like the smart student. It is a fine applied to the model every time it tries to become too complex. Example, using very large weights or coefficients. This forces the model to stay simple, general and focus only on the most important patterns in the data. Regularization can be implemented in different ways, most commonly using L1 and L2 penalties. L1 regularization, also known as lasso, penalizes the absolute values of model coefficient. One key advantage of L1 regularization is that it can shrink some coefficients completely to zero. This effectively performs feature selection, helping simplify the model. L2 regularization, also known as ridge, penalizes the squared values of coefficients instead of eliminating features. It reduces coefficient magnitudes gradually. L2 regularization is especially useful when dealing with multicollinearity, where input features are highly correlated. Choosing between L1 and L2 depends on the problem context and modeling goals. Let's summarize how we measure and manage model performance and the practical checklist for building effective machine learning models. First, the data is typically split into two parts. Training data, usually around 80%, is used to learn patterns. Testing data, around 20%, is used to evaluate predictions on unseen data. Errors fall into two main categories. Bias error occurs during training when the model cannot fit the data well. Variance error appears during testing when predictions fail to generalize. The ultimate goal is to minimize both bias and variance. Doing so leads to the best possible fit, not just for past data but for future predictions. This balance is the foundation of effective machine learning. Next, build your model by starting simple, linear or logistic models, which are often good initial choices. Always verify assumptions before increasing complexity. Evaluate the model using multiple metrics. Accuracy alone is not sufficient. Consider metrics such as F1 score, RMSE, confusion matrix analysis, and then diagnose model performance by comparing training error and testing error. High training error usually indicates underfitting, while high testing error indicates overfitting. Finally, refine the model accordingly. For underfitting, consider adding more features or reducing regularization strength. For overfitting, increase data size or apply regularization technique like L1 or L2. Remember, the best model is not the one that fits training data perfectly, but the one that generalizes effectively to real world scenarios. So let us open Jupyter Notebook and start writing some Python codes together to understand and bring the concepts of machine learning to life. Thank you.